Hey, what's up everybody? It's your personal math teacher, Mr. Boyden. I'm back with you today to look at Venn diagrams, and we're going to talk about something called inductive reasoning, which is going to be really important as we go forward and learn more math. But let's start with Venn diagrams. Now guys, I think you probably have seen Venn diagrams before, and you probably drew them like this. And it may have been something like maybe cows and people. And so maybe both have eyes, maybe both have legs. What's something that only people do? Only people speak Swahili. As far as we know, cows don't do that. Only cows moo, although I guess technically some people might moo, right? Sleep standing up, things like that. So the thing in the bubble that overlaps, these are things they have in common. And the things in the outer bubbles are things that are unique to cows and that are unique to people. So let's do another one, another example. And in this one, we will have people who do sports, who play sports, and people who are freshmen. And then usually we put a box around the outside. And so here's what I want you to think about. Depending on the location here, what does it mean? Like, if a person came up and wrote their name in here, like James, what do we know about James? James is inside of the freshman bubble, so James is a freshman. And James is inside the sports bubble, so James plays sports. What about if Keisha comes over here? And Keisha writes her name in this part. Keisha is inside the sports bubble, so she plays a sport or two. But Keisha is not a freshman. She's not inside the freshman bubble. What if I had Rodrigo over here? What do we know about Rodrigo if his name is written out here? Well, he's not inside the sports bubble, so he doesn't play sports. And he's not inside the freshman bubble, so he's not a freshman. So that's what we know. We know about what Rodrigo is not. We know he's not a freshman, and we know he does not play sports. That's what we know. So, guys, the one thing that I think is new, I don't know if you'd consider this area outside of the bubbles on a Venn diagram. Usually when I learned about these before taking like higher level math classes, it was always just you're in a bubble. But you can also just be not in any of the bubbles. That's okay. You can kind of break the mold. And that is a new thing that I want you to be aware of. Let's go do a math example. Okay, so we'll do it with geometric terms that we already know. Let's do one like this. So I'm going to start with a box, and in here I'm going to have a bubble, and that bubble is the quadrilateral bubble. And inside of that bubble, I'm going to put another bubble. This is the rhombus bubble. Let's zoom in on that so you can see it more easily. So we have a quadrilateral bubble, we have a rhombus bubble. So if I wanted something like, what are other rhombuses? You know what? A square is a rhombus. So a square is a rhombus. Is there anything else that's definitely a rhombus? I'm not sure. So what about things that are in this quadrilateral bubble that are not in the rhombus bubble? Well, how about like a trapezoid? A trapezoid, it would fit, it is inside the quadrilaterals. It is a quadrilateral, but it's not a rhombus. So it fits in here. What about parallelogram? Now I wonder, do you have any ideas about what would be on the outside of the bubbles? So not inside the rhombus bubble, not inside the quadrilateral bubble. How about like a pentagon? Because specifically right here where it says quadrilaterals, it's talking about things that have four sides. And so outside of this bubble would be anything that does not have exactly four sides, like a pentagon in this case. So let's go in the other direction. What if we had something like this? We're going to translate this one into a statement. And also, let's see if it's even true. So let's pick a spot on here. Like if I go right here, put an X. What do we know about that X? It's inside the squares bubble. And so it's a square, but it's on the outside of quadrilaterals. So what we're thinking about is a square that is not a quadrilateral. That's what this says. That is not a quadrilateral. So Can you think of any squares that are not quadrilaterals, meaning they don't have exactly four sides? No, that's ridiculous. Of course squares have four sides. That's part of what a square is. A square has to have four sides. So is this one right? No, this is not right. This is false. Let's try flipping it around, and let's find out if that makes it right. Here's what I mean. Let's draw our own. So bubble, inner bubble, and I'm going to go squares on the inside and quadrilaterals on the outside. And let's go do this exact same test again. I'm going to put an X right here. There's that X. Now that X, it's outside of the squares bubble. So we're looking for a thing that is not a square, but it's inside quadrilaterals, but is a quadrilateral. Can you think of any shapes that are not squares, but they are quadrilaterals? Oh yes, there's lots of them. How about a rectangle? So this thing right here could be a rectangle. It could be a rhombus. It could be a trapezoid. It could be in here you'd put a square. Okay, and on the outside maybe you would have a pentagon. Okay, because it's not a quadrilateral. So this statement was wrong, we've now fixed it. Okay, so guys, that's what that is. That's just practice reading and seeing what Venn diagrams are. It might be news to you that actually a bubble like this quadrilaterals one, it can be entirely inside of another bubble. But of course that's true. Like, for example, let's say that I went like this and I called this big bubble animals. Well, inside of that, I might have another bubble that's called birds. And inside of that, I might have birds that, or I might have things that don't fly. So like a seagull would be outside of that. And a bobcat would not be a bird, so it's on the outside of that, but inside animals. Birds that don't fly, how about like an emu? Or a kiwi? Or an ostrich? Or I might even have another category of birds that don't fly, but they do swim. And then I would add in penguins. So guys, I wonder if that helps you to think about it. We can have as many bubbles inside of here as we want. As long as we can keep finding things that belong inside those bubbles, you can just keep adding bubbles. So I started with the animals bubble. And then I said, okay, well, that was pretty easy. It's pretty easy to name some animals. So I thought, okay, well, maybe we could categorize. We could have birds that don't fly, and we could add on to that more specifically birds that do swim. And there might be others. Penguins is the one that I know about. So if you have others, that's awesome. Let me know, but that's what I know about. This example is just to show you that like the concept might seem foreign when it's math terms, but I think you'll understand it pretty easily if we do something you're familiar with, like birds. All right, the other thing we're talking about today is inductive reasoning, because here's an example of inductive reasoning right here. Okay, so, and we'll define it in a minute, but let's just consider the example first. Okay, we are asked to sketch the next figure in this sequence, and we need to know how many blocks are needed to do it. I'm going to pause here for a second and give you a chance to just kind of look at the pattern, notice the pattern, and see what you think the next one is. What stands out in my eyes, and you may have seen it differently, this is 3 across the bottom and 1 layer in that direction. This one goes 4 across the bottom and 2. 1, 2, 3, 4, 5. This one goes 5 across the bottom and then up 3, and this one goes 6 across the bottom and then 4. If I continue that pattern, the next one would be 5 tall, and it would be 7 long. And I also notice that 4 times 6 is 24. And 3 times 5 is 15, and 2 times 4 is 8, and 1 times 3 is 3. It's like area. So 5 times 7 is 35. So guys, that's inductive reasoning. We just looked at a pattern, and we used our understanding of that pattern to figure out what's going to come next. As humans, we are uniquely placed compared to other animals to understand patterns. Let's take advantage of that. That's why we have inductive reasoning. Okay. So inductive reasoning, that's exactly what we just did. Okay, now we did an example first because I thought that would be easier to understand, okay? All it is when you notice patterns and you make either a generalization, like, hey, this is how it works. And that's what I did up here when I said, like, oh, in general, these are going up by 1, 3, 4, 5, 6. I generalized. Okay, and then I also made a prediction. The next one would be 35. So that's inductive reasoning. Now there's another vocab term on here that I'd like you to write down. They call it a conjecture. Okay. Now you may not know the word conjecture, or you might, but if you don't, I know that you know a word that's similar. I'm pretty sure you know the word hypothesis from your science class. Okay, now in science class they call it a hypothesis. In math we call it a conjecture. I mean, the difference doesn't really matter. Okay, I mean they work the exact same way. So let's do an example of a conjecture in mathematics. And here it is. Sean looks at 3 linear pairs of angles and she notices that in every one of the cases, the linear pairs are supplementary. So what did Sean look at? Sean may have looked at something like, here's a linear pair, and maybe it was like 60 and 120, and here's another linear pair, and maybe it was 80 and 100, and then maybe a third linear pair, and it was 90 and 90. Interesting, supplementary, adding up to 180. So what's a conjecture that she could make? She's going to use inductive reasoning. She's going to say, I'm noticing a pattern here, and I'm going to make a prediction or a generalization. I'm not going to say something about a specific case, but I'm going to say something that's maybe generally true. It's my guess, my prediction about what's true. Sean might say, I think that maybe all linear pairs are supplementary. See, she only looked at 3 examples, but he goes, interesting, there's a pattern here, there's something going on here. So I think that they're all supplementary, always, no matter what. Now, do we know if that's true? Not necessarily. Just because she made a conjecture doesn't mean it's true. Guys, it works the same way in science. Just because you make a hypothesis doesn't mean it's true. But you make a hypothesis, it's like your guess of what you think is going to happen. And then you test to find out. So that's what Sean would do here. Sean would then potentially go look at some more pairs or try to write a proof and find out for sure if that's true. We're not writing proofs or testing these today, but I do want you to know what a conjecture is and how to look at a pattern and say, my conjecture is I think that maybe all linear pairs are supplementary. And then later we'll talk about how to know if it's true or not. Let's do one more example. Here's a sequence. And I'd like you to make a conjecture about what you think the pattern is. And when you think you know the pattern, then write down the next 3 terms. Please pause the video so you can try this. When you hit play, I'm going to explain how to do it. Here's the pattern that I noticed. The pattern that I noticed is that 2 to 4, it adds 2. And 4 to 7, it adds 3. And 7 to 11, it adds 4. So based on that, my conjecture about the pattern is I think it goes up by 1 every time. I think the next thing it's going to do is add 5, and the next number would be 16. I think it's then going to add 6. And when it adds 6, the next number is going to be 22. And then after that, it would add 7, and I would get 29. Okay? That's what I got. If you disagree, I'd be curious to hear why. So hopefully you got something similar. There might be another explanation that's a good conjecture too, but this is the one that was obvious to me. All right, final thing to think about. Are all conjectures that come from inductive reasoning true? We saw an example with Sean. Sean used good inductive reasoning, noticing the patterns, and came up with a conjecture that all linear pairs are supplementary. But that doesn't mean that it's true. It might be true. Because you've probably had this experience where sometimes you have really good reasoning, and you make a prediction, and your prediction is wrong. Like, maybe you thought you knew who was going to win the NBA Finals, and you had all these good reasons, and your reasons made sense, and you noticed a pattern, and you thought, well, this pattern is going to hold true, and it didn't. That can happen. Okay, you can still have good reasoning and get a wrong answer. And that's why in mathematics we use proof. Because with proof, you know for sure. Even if your reasoning is good, if you don't have proof, you don't know for sure. Okay? That's all for today's video. I hope you enjoyed it, and I'll see you next time.